Quantum theory owes its origin to the study of thermal radiation, in particular to the blackbody radiation. A blackbody is an idealized physical body that absorbs all incident electromagnetic radiation.
Blackbody radiation is the thermal electromagnetic radiation by a blackbody in thermodynamic equilibrium with its environment.
A widely used source of blackbody radiation is a small hole in a cavity with walls that are opaque to radiation.
Radiation incident on the hole will pass into the cavity, and is very unlikely to be re-emitted. Thus, the radiation exiting the hole will approximate blackbody radiation.
The thermal radiation spontaneously emitted by many ordinary objects can be approximated as blackbody radiation, such as this tungsten filament in an incandescent light bulb. The radiation behaviors of a surface are described by its spectral radiance. Spectral radiance is the power density per unit solid angle per unit frequency or wavelength, depending on whether the spectrum is taken as a function of frequency or wavelength. Kirchhoff's law of thermal radiation states that the spectrum radiance of blackbody depends upon the temperature. The total radiance, which is equal to the area below the curve, increases with temperature.
That is, hotter substances' blackbody radiation is brighter.
Meanwhile, as the temperature increases, the peak of the emitted blackbody radiation curve moves to shorter wavelengths. At room temperature, it radiates mostly in the infrared spectrum, such as the Earth's total thermal radiation. The decrease of thermal radiation of Earth compared to theoretical model is caused by the absorption by various atmospheric components such as water, carbon dioxide, and ozone. As its temperature increases, the emission spectrum extends into the visible range and emits more and more orange, yellow, green, blue light and ultimately ultraviolet. Due to the relationship between the temperature and the color of blackbody radiation, the colors of light emitted by other light sources can be categorized with the color-temperature scale regardless of their actual temperature. For example, at about 800 kelvins, the object appears dull red.
The glass-blowing temperature is between 1100 and 1300 kelvins.
At this temperature, the glass appears to be a bright orange color. At around 2700 kelvins, tungsten filament starts to emit significant amount of visible light but still emits considerable energy in the infrared range. The Sun, with an effective temperature of approximately 5800 kelvins, has an emission spectrum peaked in the central, yellow-green part of the visible spectrum, but with significant power in the ultraviolet range as well. Sirius A, the brightest star in the night sky, has an estimated surface temperature of 9940 Kelvin.
It appears to be a light blue color and emits most of its power in the ultraviolet range.
In 1896, Wilhelm Wien derived Wien's approximation from thermodynamic arguments. It does accurately describe the high-frequency spectrum of blackbody radiation, but it fails to accurately fit the experimental data for low frequency. In 1905, Lord Rayleigh and Sir James Jeans derived the Rayleigh-Jeans law based on classical physical arguments and empirical facts. It agrees with experimental results at low frequencies but strongly disagrees at high frequencies. This inconsistency between observations and the predictions of classical physics is commonly known as the ultraviolet catastrophe because predicts an energy output that diverges towards infinity as frequency tends to infinity. The Rayleigh-Jeans law revealed an important error in physics theory of the time. In 1900, Max Planck derived a formula for the blackbody radiation, known as the Planck's law.
It fits for all wavelengths of blackbody radiation spectrum remarkably well.
To give physical explanation of the law, Planck suggests that, although light are waves, its energy is carried by charged oscillators inside the cavity.
Planck called the hypothetical oscillators light quanta.
Planck explained further, the energy of a light quantum should be proportional to the frequency of the oscillator. This is known as the Planck relation.
Another scientific discovery, with which quantum mechanics began, is photoelectric effect.
In 1887, Heinrich Hertz noticed that a negatively charged object loses its charge more readily when illuminated by ultraviolet radiation.
It is called photoelectric effect and was proved to be the emission of electrons later. Electrons emitted in this manner are called photoelectrons.
In 1902, Philip Leonard observed that electrons are emitted only when the light exceeds a certain frequency, regardless of the light's intensity or duration of exposure.
Moreover, the maximum kinetic energy of photoelectrons increases with the frequency of the light. In contrast, the number of photoelectrons was proportional to the light's intensity.
This disagrees with classical electromagnetism, which predicted that the light energy would be proportional to the intensity of the radiation. In 1905, Albert Einstein published a paper advancing the Planck's light quanta hypothesis to explain experimental data from the photoelectric effect.
Einstein theorized that the hypothetical oscillators do not exist. The electromagnetic radiation itself is quantized.
The quantum of light is named photon by Arthur Compton in 1928. A photon is a particle.
The energy in each photon is equal to the frequency of light multiplied by the Planck constant. It is the same as the Planck's relation. In a metal, all the electrons have lower energy than a free electron in the vacuum, so that they are bounded in the solid stably.
The work function is the minimum energy needed to remove an electron from a solid to the vacuum. It is the difference between the energy of an electron in the vacuum and the highest energy of electron in the solid. In the photoelectric emission process, if the photon energy is lower than the work function, the electron is unable to escape the material, regardless of the intensity of light. When an electron within the metal absorbs the energy of a photon and acquires more energy than its work function, it is likely to be ejected. The energy of the emitted electrons depends on the energy of the photons, but not the intensity of the light.
The intensity of light is proportional to the flux of photons. Thus, the flux of photoelectron increases with the intensity of light.
Einstein showed that photons also carry momenta, making them full-fledged particles.
The momentum of a photon is equal to the Planck constant divided by the wavelength. And the direction of a photon's momentum is the direction of light propagation.
In 1923, Arthur Holly Compton studied the scattering of high-frequency X-ray after an interaction with a charged particle, usually an electron, known as Compton scattering. He explained the X-ray energy shift by attributing particle-like momentum to photons, so that both momentum and energy are conserved during the scattering. Compton's experiment convinced physicists that light can be treated as a stream of particle-like objects, that is, photons.
For example, given the work function of sodium, calculate the threshold frequency of photoelectric emission of sodium and the momentum of the photon. To solve it, first express the work function with SI unit.
Then, the threshold frequency of photon can be calculated with the Planck relation. Finally, the momentum of the photon can be calculated from its wavelength. But we do not need to work out the wavelength because it is expressed with frequency and ultimately the work function and the speed of light. In 1924, Satyendra Nath Bose developed the theory of the statistical mechanics of photons without using any electromagnetism, which allowed a theoretical derivation of Planck's law. Einstein showed that Bose's derivation assumed that photons are identical particles, which can aggregate in the same state within a system simultaneously. Particles with such properties are called bosons. All bosons obey Bose-Einstein statistics, which explains blackbody radiation and other phenomena like laser, superfluid helium, and Bose-Einstein condensation. In comparison, classical particles are distinguishable.
Fermions cannot occupy the same state within a system simultaneously due to Pauli exclusion principle.